In this video, we will implement the Sudoku problem that we have designed with the soft constraint on the lines and the blocks, on the columns and the blocks, and we will have as hard constraint that we have a permutation on every row from 1 to 9. And for that, we will use the constraint-based local search library that is available in the repository of the course on GitHub. This library will facilitate the development of local search algorithms. You will be able to add constraints and objective functions in your model. It will compute for you the violations, and it will compute also for you the delta, that is how much would the objective function change, for instance, if you swap the values of two variables. And thanks to this library, you can really focus on the interesting part, that is the design of the moves and the design of the heuristics that you want to have to escape the local minima. I will come back to that later, but let's first understand the magic that is provided by the solver and how to use it. So, an instance of the Sudoku will be described like this, with an array of integer, okay, like this one. And we will have a 0 for every cell that is free, and we have already a fixed value for some of the hint positions. For instance, this one will be a 1, and it should remain a 1 at the end. And we will start from an initial solution that is that one, and that one, as you can see, will agree on the hint position. For instance, you have a 1 here, and you also retrieve the 1 here. You've got a 6 here, it's also there. Then you have the 7 is there, and so every hint position you can retrieve it in this initial solution. But on every row here, you have an arbitrary decision from the values from 1 to 9, but this is a permutation, okay? This is a permutation from 1 to 9, okay? And you have a permutation like this on every row. Okay. This type of object here represents the decision variables. Okay, we have an array here that will represent the value that will be taken for every cell in the grid, and we call that an int-var local search. Then we will also have a variable that represents the total violation of the grid, and I will come back to that later. Then we have the constraint system that will aggregate all the constraints of the problem. Then we have all the possible swaps, okay, all the possible swaps between the position, and we will also pre-compute that. First, we create the solver, then we instantiate the grid, okay, and every variable here will take as initial value what we have here, okay. So this will be the initial value, and you can already realize that we initialize the grids by satisfying the hard constraints that we have listed here. Okay, so we will maintain these hard constraints always feasible. And then here we will build the constraints. So we will have one constraint for every column and one constraint for every block. And so we have overall 9 blocks. So if I split the blocks here, okay, you can see that I have 9 different blocks, and I have also 9 different columns. And so this is why here I'm creating the all different constraints on the columns, the all different constraints on the block. Okay, and so this all different constraint on the column. Okay, first you see that I'm selecting here g minus 9 plus I, which will be, I will collect here all these ones. Okay. And then all different constraints on the block that I represent in yellow will collect these variables. Okay, and it will collect them and add them here to the in the scope of the all different constraints. Then I add these two constraints to my constraints list here, and I create a constraint system that will take all the constraints that I have collected. Okay, and then out of this constraint system, I can get the violation, a variable that represents the total violation, and this is the one that we want to minimize. Okay, that's the variable that we want to minimize. As I mentioned before, we will maintain here a set of possible swaps, okay? And this will be an array list of pairs, okay? And this will be positions inside the grid that I might be able to exchange during the search for a feasible solution. So let's see how I will initialize the possible swaps and instantiate that as an array list of pairs. I will consider every line, and for every line I will consider, so I take a line of my Sudoku, okay, and I've got here 9 different cells, okay, and I will consider every possible exchange on this line, for instance, between these two positions on line L, but I will only add them if my cell is not a hint position. So if I've got a 0 somewhere, for instance, I've got a 0 here and a 2 here, then I will avoid creating this swap. Okay, I will only add swaps if it does not involve a 0, because if it is a 0, if you remember from the instance, if it is if it is a non-zero, so for instance, if you have a 6 here, it means that it is a hint position, and in that case, you don't want to consider exchange that involves a specific cell that is a hint position of the problem. So you only want to consider swaps between positions that do not involve a hint that is given in the instance. Okay, so that's the swap, the possible swap that I will. So I pre-compute all the possible swaps at the beginning here. So the first search that we will study is a pure greedy search. The pure greedy search will really try to improve the current solution greedily by always considering the best swap at the current iteration, and we will consider all the possible swaps that are available. So the search is that one, as long as I have some violation in my constraint system, as long as the violation is larger than 0, then I will do an iteration greedy, and my iteration greedy will try to find the best swap, and then we will swap between the two positions that I have found in my pair. So I will exchange the grid cell at position A and the grid cell at position B, and A and B are the two values inside my pair. Okay. And the way I will discover the best swap is simply that I will iterate over all the possible swaps that I have. If you remember from the previous slide, I have pre-computed all of them at the beginning. I consider all the possible swaps. I compute what is the delta. So how much would my objective function change if I would exchange these two variables? Okay. And if the delta is better than the best delta that I have seen so far, I store the best delta and I keep the swap here, the best swap, also as a variable here. And at the end, I return the best swap. And this is the one that I will apply here, okay? I retrieve the best swap and then I apply this swap. That's a pure greedy search, right? I'm always selecting the best move, the best exchange between the two positions. The problem if I do something that is too greedy is that I will quickly decrease my objective function, like here. I will quickly decrease, but I will be stuck at some point and I will not be able to reach the violation of 0. Okay? And this is because I'm a little bit too greedy. So if you want to be a little bit less greedy, you need to apply what we call a meta-heuristic. And one way to avoid that is also to avoid direct and short cycles and to diversify and escape from local minima. So if you want to avoid short cycles, for instance, if you have exchange A and B, you don't want to come back. So imagine that you exchange A and B, and then B and C. You don't want after that to retrieve, to cancel the move that you just did and come back in the previous situation. And this is what I mean by avoid direct and short cycles. Okay, one way to avoid that is use what we call the Tabu heuristic. It's pretty easy to understand and it's very efficient in practice. So it's always something that you should try first in your project is to apply a Tabu search in case you have local minima and you want to escape them efficiently. So the idea of Tabu search is that if from A you move to B, you will prevent the reverse move for a while. So you will prevent returning back to A for a while. You don't want don't want to visit A because you know that you have already considered that solution before, and so you want to prevent it for a given number of iterations that we call the Tabu tenure. Okay, the Tabu tenure will be how long a move will remain taboo during the search. And this will help you to accept, to degrade a little bit the solution so that you can escape from local minima and possibly reach a better global optimum, for instance. So how do we implement it in practice? In practice, if you remember the move are stored as pairs with two values A and B, and inside that one we will also store the next iteration when the move is available. Okay, that's the next iteration when the move will become available again. And so in the solve procedure, we will, instead of calling iteration greedy, we call iteration taboo. This is the Tabu tenure. It's exactly the same as before, except that we will search for the best swap that is not taboo, okay? And we give in argument the current iteration number, and then we apply the swap, okay? And then we will say that the swap that we just applied, it will remain taboo until the current iteration number plus some random number that we will sample here from a random number generator. Okay, and so if your current iteration number, for instance, let's assume that iter is 10, okay, and the next random number that you have generated is 5, it means that for 5 iterations, this move that you just applied will remain taboo. You cannot select it until iteration becomes 15. Okay? And so when you will select the best swap, of course, you will consider the taboo that you have stored inside the pairs. So you will consider all the possible swaps, but only the ones that have a stored iteration number that is less than the current number of iteration that you have. Okay, and so if that one, for instance, here is 15, it means that you can only select it starting from iteration 15 and the current iteration number is 11, then this move is taboo and it will not be considered by this procedure that is looking for the best swap that is not taboo. If you do that, the landscape of the objective function is quite modified, right? You will see that you will degrade much more the objective function and you will see something like this. And at some point, quite quickly, you will reach the optimal value, so the violation of 0. Okay, I advise you to play a little bit with the code to execute it and experiment yourself a little bit the impact of this taboo tenure, for instance, that you have here. Okay, how long it will remain taboo. This might have quite an impact on the search in practice. Some possible improvements on this procedure is you might consider adding an aspiration criteria. It means that you will maintain the current best violation and you will say that a move is taboo unless it can lead to an even better solution that you have seen so far. Okay, so that's a quite efficient way to avoid the taboo to be a little bit stupid, if you want, because the taboo search might say that I don't want to apply a move even if it will allow me to reach the best solution that I have seen so far. Okay, and so if you include an aspiration criterion, then you will be a little bit less stupid. The restart is also a good strategy. It means that on every iteration, you might introduce some random permutation. So you will shake a little bit everything by randomly perturbating the solution. And if you want, it's a kind of soft restart. Okay, you simply just perturbate a little bit because maybe you might be stuck after, let's say, 1,000 iteration. Every 1,000 iteration, you may want to restart a little bit by including random perturbation. Okay, that's also quite effective in practice to do that.